So let's then deal with supplemental problem 5.9. You can find this problem in the course ebook in the Chapter 5 Supplemental Problems on page 12. Given this one inductor circuit with a switch, can you find the current I of t for all time? As we showed in the Chapter 5 lecture notes, a one inductor circuit with switches can be analyzed with the same 6-step algorithm we use for capacitors. Let's solve for I of t. Step 1 is to formulate the equations. I of t is a first-order differential equation of sum a plus b times e to the minus quantity t minus t0 over tau. This switch is going to close at t equals 0. T0 is equal to 0. Step 2 is to find the pre-switching conditions. Find the current in this resistor when the switch is open for a long time. As we showed in the Chapter 5 lecture notes, an inductor in a DC circuit for a long time looks like a short circuit because V is equal to L di dt. If the current isn't changing with time, its derivative is 0. The current in the inductor is the current in our 4K resistor. That is our I of t. Current that's flowing is 16 volts divided by 8K, or 2 milliamps. Step 3 is to find the initial conditions. And the inductor current is the current that we're solving for. And the value was 2 milliamps before the switch changed state. And now when the switch changes state, the current is still the same. Go back up here. And now this switch is going to close at t equals 0 and short out this resistor. But the current that's here was 2 milliamps prior to that switching. And so it still is 2 milliamps. That's going to be our a plus b times e to the 0. Next, we'll find the final conditions. When an inductor is in a circuit for a long time, it looks like a short circuit. This is also shorted. The 16 volts is across the 4K resistor. 0 volts here, 0 volts here. So the current that's flowing in here, through here, through here, is going to be 16 volts divided by 4K, or 4 milliamps. And that's going to be a plus b times e to the minus infinity, or just a. Step 5 is to find the Thevenin resistance seen by the inductance. We'll set all the independent sources equal to 0. The switch has changed state, so it's a short here. Looking back, I see a short in parallel with 4K. That's just going to be 0 times 4K over 0 plus 4K, where 0. So all we see looking back is just this 4K resistor. Our time constant is L over R Thevenin. L was 500 millihenries. R Thevenin was 4K. That gives us 125 microseconds. Then lastly, put it all together and find the solution in step 6. A plus B was 2 milliamps. A was 4 milliamps, so B must be equal to minus 2 milliamps. I of t is A plus B times e to the minus t over tau. 4 milliamps minus 2 milliamps times e to the minus t over 125 microseconds. And the units are amps. And this is valid for t greater than 0, but also equal to 0, because this is also the current in the inductor. We found that when t was less than 0, the current was 2 milliamps. We just check when t is equal to 0, we're going to get 4 milli minus 2 milli times e to the 0, or just 2 milli. Current in our circuit is continuous as we pass through the switching state at t equals 0. And this is supplemental problem 5.9.